All right, so let's tackle these circuit problems here. And really the first thing you want to keep in mind is you want to use what we call Ohm's law. Okay, so you want to use Ohm's law. And this is so useful for figuring out a lot of things when it comes to like the loads that you're dealing with. So Ohm's law relates voltage, current, and resistance. Okay, so if you have two of these, you can always find the third one. So if you have the volts, if you have the current, say I, you can rearrange this for finding the resistance. So any sort of variable you want to find here, as long as you have two, you can find the remaining one with some basic algebra. The next thing you want to keep in mind is Kirchhoff's current law. Okay, so Kirchhoff's current law states that current that enters a junction, it has to be the same before you go in and after you leave. Okay, so in a loop like this, our current, there really is only one path for that current to go. So this is a series circuit, so it's going to be the same all throughout. Okay, this Kirchhoff's current law, especially when we get into multiple paths like parallel circuits, current's gonna split up. Okay, and we're gonna find that current, electricity, likes to go down the path of least resistance. Okay, and that's gonna play a role when we take a look at the resistors and what their resistance values are, and you're gonna see how current's gonna split. Okay, and yeah, so any current in a closed loop here is going to be the same. There's also Kirchhoff's voltage law. Okay, so essentially we start with a battery at the beginning here, and this battery is able to provide 90.0 volts, and this battery is essentially, you could view it almost like a pump that makes these electrons go around the circuit. Okay, it gives those electrons energy, it boosts them up to a higher energy level, and that allows those electrons to do work, right? It could be, powering a light bulb or going through a resistor, right? And releasing that energy as heat. It allows it to do work, okay? And essentially what this law is saying is that if we start with 90 volts here, right? The sum of all the voltage drops across these loads, like this resistor here, has to equal 90. Okay, so we haven't done it yet here, but if we had one resistor here, one here, let's say hypothetically this one had a voltage drop of 45, and then this one would also have to be 45, because 45 and 45 gives you 90. But we're going to calculate that exactly for this one here. All right, so enough yap there. I am going to start this problem like I start every problem, and I'm going to list out the stuff we want to find. So we want to find V1, we want to find V2, we want to find I0, also known as I0, it's like the initial current, and we want to find our, let's say I1, good, and we have our R2 that we got to find. Okay, so we don't know what any of these are as of late, but we'll figure that out pretty soon. When you're dealing with problems like this, you want to just break it down into little tiny pieces. Okay, just consider the stuff you have, and then just try to systematically eliminate what you don't have when we find these. Okay, so like I said, with Kirchhoff's current law, we're dealing with a series circuit here. So his law states that the current has to be the same in this closed loop here. So if that's the case, if we have I2 equals 4.5 amps, that's going to be the same throughout the whole entire circuit. So, and also maybe you're a little bit kind of confused about these arrows. So these diagrams are actually set up for conventional current. So we can actually just reverse these this way. No big deal, and we'll get the same answers anyway. So this would be like our negative end of the battery, this would be positive. The reason why these diagrams are set up this way is because conventional current diagrams like these were were analyzed prior to understanding what an electron is. You know, they actually believed it was the flow of positive charges going this way. That's why these arrows were initially pointed in that direction. But then later the electron was discovered, you know, far after we were working with electricity, and we know that electron flow is going to come out of this negative end and go around there. So any of those arrows that you see here, you can just reverse them. All right, so where were we? Okay, so we know current here is going to be the same throughout. So we got I2 equals 4.5 amps, and we know we have an initial current over here. This is before it even gets into our first load there. That's going to be I naught, and you know there's going to be a current that is, of course, after that is going to be I1, and these are super easy to find out because we know that our current that we start with here is going to be equal to this current, and it's going to be equal to this current because it's all the same throughout this closed loop. Okay, so we immediately know that I naught is going to be 4.5 amps. Okay, and for I1, that's also going to be 4.5 amps. Cool. So that's great. Now, what do we want to tackle next? So we want to figure out what R2 is, for sure. And I'll just kind of put R2 over here. We don't know what that is yet. And we want to figure out our voltage drop over 1. So if this is R1 here, we want to calculate our voltage drop. And if we were to even build the circuit in real life, okay, we would actually calculate our voltage drop across this. So we'd have to wire our voltmeter in parallel. So it would be in parallel to this resistor here. So this would be considered V1. So to figure out what V1 is, okay, we have to use our Ohm's law. Okay, so V1, sorry, my marker's a little bad here. V1 is equal to I1 times R1. Okay, I'm gonna use a different marker here. So we know what I1 is, and they also give us the resistance of this resistor that's in the way there. Okay, so we can just plug those values in. So we can find V1. Oh, another bad marker. Love that. Well, we're gonna just persevere here. Okay, so we got V1 is going to be equal to 4.5 amps. Okay, and we have our resistance here. That's going to be the 12 ohms here. Okay, that's just the Greek letter omega here. Kind of looks like a little Lululemon symbol, right, for their company logo. And we're gonna just multiply these together, right? And you'd find we multiply 4.5 times 12, that's going to give us 54 volts, okay? So we know that this battery initially charged up those electrons, so they'd be at 90 volts, like right here. And then as it passed over this resistor, that energy is going to get used, it's going to dissipate as heat. So it gets used up, and it's specifically used up 54 volts. Okay, 54 volts. Okay, and this is going to give us a hint for V2 as well. So we know that V1 is 54 volts. Okay, so according to Kirchhoff's voltage law, so the sum of all these voltage drops that we see in this loop here, they all have to equal what we started with. So that would be the 90 volts that the battery provided. And this is really linked in with the law of conservation of energy, right? So we can't just, create energy out of nowhere. Okay, it has to come from somewhere. It's coming from this battery. Then as it goes around, okay, so we ended up dropping 54 volts here. But then you got to think, so how many volts are we going to drop over here. And let me do my voltmeter here in parallel. So what are we gonna get there? Well, we simply just have to we're taking our 90 minus our 54, and that's gonna give you 36 volts, okay? So one way you can write that is you can kind of write it like this. You could say V initial, V naught, is equal to V1 plus V2. And this is our Kirchhoff's voltage law, okay? So we know that this is going to be 90, okay? We got our V1, which we just calculated. That's going to be 54 volts, okay? Plus V2, and we know simply with simple math here, right, we're going to rearrange for V2, and if we subtract, let me use a different color here. So if I'm subtracting, 54 from both sides here, okay, so over here as well, so these are going to go away, and then we're left with simply our V2 is equal to 90 minus 54, and this is going to be our 36. Cool. Okay, so we got V2. That's going to be 36. Awesome. And really, these circuit props are done in the same way like this, right? Like doesn't matter how complex they are, because you're going to see with problem 5 and 6, they get a little more complex. But if you just analyze it step by step, you can figure out how to do this, okay? And I don't want this video to get too long here, but I'm almost done. Here we go. So now we got to find R2. And R2, again, simple. We want to spam our Ohm's law, right? We definitely want to spam our Ohm's law here. So R2, so we're going to use, so we're using Ohm's law, and we're going to go V2 equals I2 times your R2, okay? So we got to consider what we have here. We're trying to find R2, so I'm going to rearrange our equation here for R2. I'm going to divide by, right, I want to do the opposite of multiplication here, so I got I2 times R2, so I got to divide by I2 on both sides, right, just simple algebra, and we know R2 is going to be V2 over I2. Okay, so we got R2 is going to be V2 over I2, and we know what V2 is. V2 is right here, so we got our 36. Okay, so we got our 36 volts, and this is going to be over our I2. Okay, and I2 is just simply given in the question, which is great. That's going to be 4.5 amps. Okay, and then R2, and if we did the math on this one, this is going to give us, what do we got there? We got 8. Okay, so we got 8 ohms there. If you really wanted to be a stickler here, we want to do sig figs. I didn't teach you what sig figs are yet, but we're going to do that in kinematics when we cover that. And yeah, this would technically be, if you want to be a stickler, 8.0 ohms. You're probably like, oh, what's the difference, right? 8 and 8.0. But with significant figures, you're going to find out shortly, maybe the topic of a future video, that these are in fact, treated differently in physics. Anyway, hopefully that wasn't too long, but that's how we figure out all of our answers for this one. And just to validate, you can see how they match the bottom of the page. You can take a look there. So we have, okay, so we're looking at, 54, 36, we got 4.5, and 8, or 8.0. Anyway, hopefully the rest are okay for you, and worst case, I could always make another video, no big deal, but they're really just handled the same way. Remember your Ohm's law, your Kirchhoff's current law, and Kirchhoff's voltage law. Go back to the lesson and really just think about those concepts, understand the foundations, and then life's going to be easy when it comes to solving these circuits. All the best.